Imagine volunteering your unborn great-great-grandchildren for a prison sentence they never agreed to, inside a sealed metal world they can never leave, hurtling through radiation-soaked darkness toward a star none of them will remember choosing. That is a generation ship. Not the gleaming arc of science fiction, not a noble colony vessel gliding between stars. A generation ship is a closed civilization locked inside a container, asked to function perfectly for longer than the Roman Empire lasted, with nothing coming in from outside and no door back to Earth. The largest sealed ecosystem ever built on Earth began collapsing within months and barely lasted 2 years before requiring outside rescue. A generation ship would need to sustain one for centuries. The engineering is not the hardest part. Keeping humanity itself from falling apart is. And the real numbers are worse than you think. If you enjoy journeys that completely reshape how you see humanity's future in space, do me a favor and hit that like button and subscribe. It genuinely helps this channel keep bringing you stories like this one. Now, settle in, get yourself comfortable. Let's begin. The nearest star to our sun is trying to kill your imagination, not through hostility. Through distance, Proxima Centauri sits 4.25 light-years from Earth. That sounds manageable if you have never converted a light-year into something your brain can actually process. 1 light-year equals roughly 5.88 trillion miles. Multiply that by 4.25, and you arrive at a number that stops meaning anything to the human mind. Approximately 25 trillion miles of emptiness separate us from the closest star that is not our own. 25 trillion miles of vacuum, radiation, and cold so absolute that the background temperature of interstellar space hovers just a few degrees above the point where all molecular motion ceases. NASA's Voyager 1 spacecraft, launched in 1977, is the farthest human-made object from Earth. It has been flying through space for nearly 5 decades, traveling at roughly 38,000 miles per hour. At that speed, Voyager 1 would need over 73,000 years to reach Proxima Centauri. 73,000 years. When Voyager 1 launched, the internet did not exist. 73,000 years ago, anatomically modern humans had not yet left Africa for Europe, and Neanderthals still had the continent to themselves. The entire span of recorded human civilization, every empire, every revolution, every cathedral and satellite and smartphone, fits inside the last 5,000 years. Voyager would need to fly for 14 times the length of all recorded history to reach our nearest stellar neighbour. And Proxima Centauri is not even an interesting destination. It is simply the closest one. This is the wall that generation ships were invented to climb, not a wall of engineering difficulty or political will, a wall of time. Human beings live approximately 70 to 80 years on average. Even the most optimistic projections for human lifespan extension do not push that number past 150. Interstellar distances demand travel times measured in centuries or millennia using any propulsion system that obeys known physics. The gap between a human lifespan and the duration of an interstellar voyage is not a technical inconvenience. It is a categorical impossibility. No single crew can survive the journey. Not because the ship would fail, because the crew would die of old age long before arrival. Faster travel would solve this problem, but faster travel does not cooperate with physics. To reach Proxima Centauri in a single human lifetime, a spacecraft would need to travel at a significant fraction of the speed of light. 10% of light speed, roughly 67 million miles per hour, would bring the journey down to about 42 years. That is within a human lifespan. But accelerating a crewed vessel to 10% of light speed demands energy on a scale that dwarfs anything humanity has ever produced. The kinetic energy required to push even a modestly sized spacecraft to that velocity exceeds the total energy output of every nuclear weapon ever built, combined by orders of magnitude. And that accounts only for acceleration. You also have to decelerate at the other end, which requires the same amount of energy again. The fuel problem alone is catastrophic. Conventional chemical rockets cannot achieve these speeds regardless of how much propellant you carry, because the weight of the fuel itself demands more fuel to carry it, creating a diminishing return spiral that collapses into absurdity long before you reach interstellar velocities. Scaling this to carry human beings multiplies energy requirements by factors so vast, the idea transitions from ambitious to fantastical. The physics works for postage stamps. It does not work for people. This leaves three options for getting humans to another star. The first is cryogenic sleep, freezing the crew and reviving them at the destination. The problem is that reliable, reversible human cryopreservation does not exist. No human being has ever been frozen solid and brought back to life. Vitrification techniques show some promise for preserving individual organs, but scaling this to an entire human body and successfully reviving it after decades or centuries remains firmly in the realm of speculation. It is not a technology that is almost ready. It is a technology whose fundamental feasibility has not been demonstrated. The second option is relativistic travel, pushing the ship fast enough that time dilation becomes significant. A crew traveling at 90% of light speed would experience the journey to Proxima Centauri in less than 2 years of subjective time. But achieving 90% of light speed brings back the energy problem multiplied by relativistic mass increase. The closer you get to light speed, the more energy each increment demands, climbing toward infinity as you approach the limit. Relativistic travel is permitted by physics but forbidden by energy budgets. The third option is the one that sounds the most reasonable, precisely because it demands no new physics and no speculative technology. Instead of making the journey shorter, you accept that the journey is long and design around it. You build a ship large enough to sustain a human population indefinitely. The crew lives, works, reproduces, raises children, grows old, and dies aboard the vessel. Their children do the same, and their children after that. Generation after generation lives and dies in transit until, perhaps centuries later, descendants of the original crew arrive at the destination. This is a generation ship, and on the surface it appears to be the most elegant solution to the interstellar distance problem ever conceived. The logic is seductive. You do not need to break the laws of physics. You do not need to invent suspended animation. You do not need to produce energy equivalent to the output of a star. You simply need to build a vessel that can sustain life for a very long time and fill it with people willing to start the journey knowing they will never see the end. The problem of distance becomes a problem of patience. The problem of speed becomes a problem of sustainability. Instead of fighting time, you surrender to it. You let time do the work while the ship crawls between stars at whatever modest velocity current or near-future propulsion can achieve. At 1% of light speed, approximately 6.7 million miles per hour, the journey to Proxima Centauri would take roughly 425 years. That is approximately 17 human generations at 25 years per generation. Long, but not inconceivable. Civilizations have lasted longer. Religions have endured longer. Family lines have persisted longer. Surely a well-designed, well-provisioned ship could hold together for 17 generations. The ancient Egyptians maintained a coherent civilization for over 3,000 years. The Catholic Church has operated continuously for nearly 2 millennia. If human institutions can persist for centuries on Earth, why not aboard a ship? This reasoning sounds airtight. It is the reason generation ships have captivated science fiction writers, futurists, and even serious researchers for nearly a century. The concept first appeared in recognizable form in Robert Goddard's notes from 1918, was explored in fiction by Don Wilcox in 1940, and was given rigorous treatment by scientists at the British Interplanetary Society in the 1980s and 90s. The idea keeps returning because it seems to solve the unsolvable. It turns the most daunting problem in space exploration into a question of engineering scale. Build a ship big enough, stock it well enough, populate it wisely enough, and the stars become reachable. But here is where the seduction becomes a trap. The moment you accept the generation ship concept, you have not simplified the problem. You have exchanged one impossible challenge for a different impossible challenge that merely looks more approachable from a distance. Consider what a generation ship actually requires. It is not a large spacecraft with extra bedrooms. It is a fully closed, self-sustaining world that must recycle every molecule of air, every drop of water, every gram of nutrient, every unit of waste without significant loss. for centuries. Nothing can be imported. Nothing can be restocked. The ship carries everything it will ever have on the day it launches. Every atom of oxygen the 15th generation breathes must have been aboard since departure. Every calorie the 10th generation eats must trace back to agricultural systems established before their great-great-great-great-great-grandparents were born. On Earth, ecological recycling is handled by a biosphere that took billions of years to evolve, spans the entire surface of the planet, and involves trillions of organisms interacting across thousands of interconnected cycles. When one part fluctuates, other parts compensate. Forests absorb excess carbon dioxide. Oceans buffer temperature changes. The system is not designed. It is evolved. It is messy, redundant, and sprawling. And those qualities are precisely what make it resilient. A generation ship must replicate the essential functions of this planetary biosphere inside a sealed container. It must grow food, regenerate oxygen, purify water, decompose waste, and maintain atmospheric chemistry within habitable parameters using artificial systems that cannot rely on planetary scale buffers. If the oxygen generation system underperforms by 2% for a decade, the cumulative deficit becomes a crisis. If a crop blight eliminates one staple food source, the nutritional architecture of the entire population shifts. If a microbial imbalance disrupts the waste processing cycle, toxic compounds begin accumulating in the air and water supply, with no external reservoir to absorb them. The most ambitious attempt to build a closed ecological system on Earth was Biosphere 2, a 3.14-acre glass enclosure in the Arizona desert that sealed 8 crew members inside from September 1991 to September 1993. Biosphere 2 contains 7 biome areas including a rainforest, an ocean, a savanna, a marsh, and an agricultural zone. It was designed to be completely self-sustaining, recycling all air, water, and food without external inputs. It began failing within months. Oxygen levels dropped from the normal 21% to approximately 14%, equivalent to conditions at an elevation of roughly 14,000 feet. The cause was unexpected. Microbes in the soil consumed oxygen faster than the plants could replenish it, and the excess carbon dioxide reacted with exposed concrete in the structure, locking away both carbon and oxygen in calcium carbonate. The crew experienced chronic fatigue, impaired cognitive function, and difficulty performing physical tasks. Crop yields fell below projections, leaving the crew perpetually hungry. 19 of 25 vertebrate species went extinct inside the enclosure. All pollinating insects died. Cockroaches and certain ant species thrived. The system did not reach equilibrium. It lurched from one imbalance to another, each correction revealing new instabilities. Eventually, outside air had to be pumped into Biosphere 2 to prevent the oxygen deficit from becoming life-threatening. This single intervention effectively ended the experiment's status as a closed system. The most sophisticated sealed biosphere humanity has ever constructed could not sustain 8 people for 2 full years without external rescue. A generation ship would need to run a comparable system, likely far more complex, to support hundreds or thousands of people, for not 2 years but 200, or 400, or 1,000. And unlike Biosphere 2, there would be no emergency air supply waiting outside. There would be no technicians on the other side of the glass who could crack a seal and pump in oxygen. There would be no Earth. There would be nothing outside the hull but interstellar vacuum stretching for trillions of miles in every direction. This is the first fracture in the beautiful logic of the generation ship. The concept assumes that a closed ecological life support system can be made reliable enough to operate for centuries. No such system has ever been demonstrated at any scale for any duration remotely approaching what a generation ship would require. The longest continuously crewed habitat in space is the International Space Station, which has been occupied since November of 2000. But the ISS is not a closed system. It receives regular resupply missions carrying food, water, spare parts, and equipment. Its atmosphere is supplemented from pressurized tanks. Its waste is ejected or returned to Earth. The ISS depends on a constant lifeline to the surface. Cut that lifeline, and the station becomes uninhabitable within weeks. But the ecological challenge is only the entrance to the labyrinth. Beyond it waits a cascade of compounding burdens that most generation ship proposals acknowledge only in passing, if they acknowledge them at all. A generation ship is not a spacecraft with a very long mission. It is a civilization. The difference matters enormously. A spacecraft has a crew. A civilization has a population. A crew follows orders and maintains discipline through hierarchy and shared training. A population contains children who did not volunteer, teenagers who rebel, adults who disagree about governance, and individuals whose ambitions conflict with the collective mission. A crew can be selected for psychological resilience and technical skill. A population includes the full spectrum of human temperament and motivation, because you cannot screen for cooperation across centuries of descendants. The moment you accept that a generation ship will carry multiple generations, you accept that most of the people aboard will not have chosen to be there. The founding generation volunteers. Their children are born into the mission. Their grandchildren inherit it. By the 5th or 6th generation, no one aboard has any personal connection to Earth, to the original mission planners, or to the destination star. They were born on the ship, and they will die on the ship. The mission is not their dream. It is their circumstance. They are, in the most literal sense, prisoners of a decision made by ancestors they never knew, locked inside a world they cannot leave, travelling toward a place that means nothing to them beyond inherited dogma. This raises a question that no amount of engineering can answer. What compels Generation 9 to continue a mission that Generation 1 began? On Earth, institutions persist across centuries through a combination of cultural inertia, legal frameworks, economic incentives, and the simple fact that people can leave if they want to. A nation endures partly because its citizens choose to remain, and partly because the surrounding nations provide alternatives. Aboard a generation ship, there is no alternative. There is no neighbouring country. There is no emigration. There is only the ship, the mission, and the void. This is not stability. It is captivity. And captive populations throughout human history have demonstrated a consistent tendency toward either revolt or despair. The ethical dimension of this captivity is unlike anything human philosophy has previously been asked to address. Every generation ship proposal implicitly assumes that one generation of humans possesses the moral authority to permanently constrain the lives of every subsequent generation born aboard. The founding generation makes the decision to launch. They accept the risks. They believe in the mission. Their consent is real and informed, but their children's consent is not. Their grandchildren's consent is not, and the consent of every generation thereafter is not merely uninformed but structurally impossible, because those people do not exist at the time the decision is made. On Earth, societies routinely make decisions that affect future generations. Constitutions are written, infrastructure is built, environmental damage is inflicted, national debts are accumulated. But in every terrestrial case, future generations retain the power to alter, reverse, or abandon the commitments imposed by their predecessors. A constitution can be amended. Infrastructure can be demolished and rebuilt. Environmental damage can be remediated, at least partially. Debts can be restructured or defaulted upon. The fundamental freedom of future generations to choose differently is preserved even when present generations make binding decisions, because the world remains open and alternatives remain accessible. A generation ship eliminates this freedom entirely. The descendants cannot amend the decision to launch because the launch is irreversible. They cannot choose an alternative path because no alternative path exists. They cannot exit the community, seek a different life, or opt out of the mission's requirements. Their reproductive choices may be constrained by population management protocols. Their career options may be dictated by the ship's labour needs. Their daily routines may be governed by resource allocation schedules they had no voice in creating. They are, in the most literal sense, born into a life sentence imposed by ancestors who believed the mission justified the imposition. No ethical framework in the Western philosophical tradition comfortably accommodates this degree of intergenerational binding. Utilitarian calculations might justify the mission if the long-term benefit of establishing a human colony at another star outweighs the suffering imposed on intermediate generations. But this calculation requires assigning a value to the welfare of people who do not yet exist and comparing it against the concrete suffering of people who do, a comparison that utilitarian philosophy has never resolved satisfactorily. Deontological ethics, which emphasize the inherent rights of individuals, would struggle to justify a project that permanently strips autonomy from people who cannot consent. Virtue ethics might frame the mission as an expression of human courage and aspiration, but would need to account for the fact that the courage belongs to the founding generation, while the suffering belongs to their descendants. The generation ship forces a confrontation with a question that terrestrial ethics has had the luxury of avoiding. What do the living owe the unborn? And more disturbingly, what are the living permitted to impose upon the unborn? On Earth, this question is buffered by the openness of the world. Future generations will inherit our environmental damage, but also our accumulated knowledge, our institutions, and the freedom to reshape both. Aboard a generation ship, future generations inherit a sealed world with fixed boundaries, fixed resources, and a fixed trajectory. They inherit constraint without freedom, obligation without choice, a mission without consent. Some generation ship theorists have proposed that the ethical dilemma can be mitigated by designing the ship to be sufficiently comfortable that its inhabitants would not wish to leave even if they could. This argument has a troubling structure. It is essentially the argument that a cage is acceptable if the cage is pleasant enough. It assumes that comfort substitutes for autonomy, that material satisfaction replaces the freedom to choose one's own path. History suggests otherwise. Gilded cages produce their own forms of resentment, and the knowledge that one cannot leave transforms even luxury into confinement. Others have proposed that the mission itself provides sufficient meaning to justify the imposition, that being part of humanity's greatest adventure compensates for the loss of individual freedom. But meaning cannot be imposed from outside, it must be felt from within. And the seventh generation, born into a world they never chose, travelling toward a destination they have never seen, may not experience the voyage as an adventure at all. They may experience it as an inheritance they never asked for, a burden placed upon them by people who are long dead and beyond accountability. But set aside the social dynamics for now. Set aside the psychology, the governance, the generational resentment. Focus only on the physical container. The ship itself must be engineered to a standard that has no precedent in human construction. Every structural component, every hull plate, every seal, every pipe, every wire, every pump, every valve, every circuit board must function reliably for centuries, not with scheduled maintenance from a manufacturer, not with replacement parts ordered from a supply chain, with whatever the ship carries at departure and whatever the crew can fabricate on board. Modern naval vessels, among the most durable machines humanity builds, have operational lifespans of 30 to 50 years with constant access to dry dock facilities and global supply chains. An aircraft carrier requires thousands of skilled workers at dedicated shipyards for periodic overhauls. A generation ship would need to operate for 10 to 20 times the lifespan of an aircraft carrier without ever visiting a dry dock. Its crew would need to manufacture replacement parts from raw materials carried aboard, using fabrication equipment that itself degrades over time and must also be maintained and eventually replaced. This creates a recursive maintenance problem. The machines that fix the ship also break. The machines that fix those machines also break. At some point, you reach a layer of tooling that cannot be replicated aboard the ship, and when that layer fails, the entire maintenance cascade above it begins to collapse. Materials degrade, metals fatigue, seals harden and crack, lubricants break down, electronics corrode, radiation damages circuitry, micrometeorite impacts accumulate, each one weakening the hull by a fraction so small it is invisible in the short term, but potentially catastrophic over centuries. A generation ship does not face a single dramatic failure. It faces the slow, patient erosion of every physical system on board, spread across a timescale long enough that no individual crew generation can observe the full trajectory of decline. And yet, despite all of this, generation ships continue to appear in serious scientific literature as the most viable path to interstellar settlement. The Initiative for Interstellar Studies, a UK-based non-profit, launched Project Hyperion in 2024 as a design competition inviting interdisciplinary teams to envision generation ships for a 250-year journey to a habitable exoplanet. The competition attracted entries from around the world. The winning design, called Chrysalis, proposed a cylindrical vessel approximately 36 miles long, carrying up to 2,400 people, with rotating sections for artificial gravity and integrated agricultural systems for food production. The competition had specified a population of 500 to 1,500, but the Chrysalis team argued that a larger population improved long-term social and genetic viability. The competition judges evaluated entries on engineering feasibility, social planning, cultural sustainability, and governance structures. The very existence of this competition reveals something important about where the scientific community stands on generation ships. The concept is taken seriously enough to attract institutional support and rigorous interdisciplinary analysis. But the competition criteria also reveal the depth of the challenge. Entrants were judged not only on propulsion and life support, but on how their societies would preserve knowledge, transmit culture, maintain governance, and handle psychological stress across centuries. The competition implicitly acknowledged what the elegant concept tries to hide, that a generation ship is not primarily an engineering problem, it is a civilization problem. And civilization problems do not have engineering solutions. You cannot weld social stability into a hull plate. You cannot install cultural continuity as a software update. You cannot bolt generational purpose onto a reactor housing. The physical ship is the easy part. Not easy in an absolute sense, but easy relative to the staggering difficulty of what happens inside it once the engine ignites and Earth disappears behind a wall of accelerating darkness. Every generation ship proposal eventually confronts this asymmetry. The hardware can be designed on paper. The software of human civilization cannot. And the silence surrounding that gap is where the real story begins. The generation ship is not a solution to the problem of interstellar distance. It is a transformation of that problem into something far more complex, far more fragile, and far more likely to fail in ways that no blueprint can prevent. The distance between stars is vast, but the distance between launching a sealed civilization and successfully sustaining it for centuries may be vaster still. What comes next reveals exactly how harsh that transformation becomes once you stop imagining the ship and start calculating the physics of what happens inside it. The ship has launched. Earth is gone, not hidden behind a cloud or obscured by distance in the way a coastline disappears from a departing vessel. Gone in a way that has no terrestrial equivalent. Within months of departure, the sun shrinks to a bright star indistinguishable from thousands of others. Within years, it becomes just another faint point in a field of faint points. The ship is now the only world its passengers will ever know. Everything they breathe, everything they drink, everything they eat must come from systems sealed inside the hull at the moment of departure. Nothing enters. Nothing can be requested. The nearest rescue is receding behind them at whatever fraction of light speed the engines achieved, and with every passing hour, the energy cost of turning around and going back grows more prohibitive than continuing forward. There is no return threshold that is ambiguous. Within the first decade, return becomes practically impossible. The ship is committed, the people inside are committed. And from this moment forward, every atom of oxygen, every molecule of water, and every calorie of food aboard is all there will ever be. This is where the engineering reality of a generation ship departs from every other machine humanity has ever built. A submarine can surface, a space station can be resupplied, an Antarctic research base can be evacuated. A generation ship operates under a constraint that has no precedent in the history of technology: total material closure over centuries. The technical term is a bioregenerative life support system, and the concept is straightforward to describe but nightmarish to execute. Plants convert carbon dioxide into oxygen through photosynthesis while simultaneously producing food. Human and organic waste is decomposed by microbial systems and recycled into soil nutrients and water. Water is purified through filtration, condensation, and biological process, so only the atmosphere is monitored and adjusted to maintain the narrow band of gas concentrations compatible with human survival. Approximately 21% oxygen, less than 1% carbon dioxide, a balance of nitrogen, and controlled humidity. On paper, the cycle is elegant. Carbon, water, and nitrogen each circulate through closed loops, atmosphere to plants, to humans, to waste, to microbes, and back. Nothing is consumed in the chemical sense. Everything is transformed and returned. A well-designed bioregenerative system could theoretically operate indefinitely because it does not deplete its inputs. It merely rearranges them. In practice, the word theoretically does catastrophic work in that sentence. Real bioregenerative systems do not close perfectly. They leak, not through dramatic hull breaches, but through thousands of tiny inefficiencies that accumulate over time. Every airlock cycle loses a trace amount of atmosphere. Every water purification pass leaves behind a fraction of contaminants that gradually concentrate. Every biological decomposition cycle produces trace compounds that are not fully broken down and slowly build up in the soil, the water, or the air. These losses are individually negligible. Over weeks or months, they are unmeasurable. Over decades, they become noticeable. Over centuries, they become existential. Consider oxygen. The human body consumes roughly 350 litres of oxygen per day at rest, and considerably more during physical labour, with a working population averaging closer to 500 litres per person daily. A population of 1,000 people engaged in the constant physical work that ship maintenance demands consumes approximately 500,000 litres of oxygen daily. This oxygen must be replenished entirely by photosynthesis, because there is no external atmosphere to draw from. The plants that generate this oxygen require light, water, carbon dioxide, nutrients, and stable growing conditions. If crop yields drop by even a few % due to a plant disease, a soil nutrient imbalance, or a lighting system malfunction, the oxygen budget tightens immediately. The crew does not get to breathe less. Their metabolic demand is fixed by biology. The gap must be closed by the system, and if the system cannot close it, oxygen concentration begins falling. We already know what happened when Biosphere 2 attempted exactly this kind of atmospheric balance. Oxygen plummeted, carbon got locked into concrete, and the world's most sophisticated sealed ecosystem nearly killed its crew within 2 years. But the specific lesson for a generation ship is even worse than the headline failure suggests. Biosphere 2's atmospheric crisis was identified, diagnosed, and understood because the team had external communication with scientists on the outside. They could discuss the problem with atmospheric chemists and ecologists who were not trapped inside the enclosure. They could consult published research. They could receive analytical instruments that had not been included in the original design. And ultimately, they could pump in outside air to prevent the crisis from becoming fatal. A generation ship crew facing an equivalent atmospheric anomaly would have none of these advantages. They would need to identify the problem using only the diagnostic tools aboard. They would need to determine the cause using only the scientific expertise present in the current generation. They would need to devise and implement a solution using only the materials and equipment carried since departure. And they would need to do all of this before the oxygen deficit reached lethal levels, with no external consultation and no emergency air supply. The Biosphere 2 failure was recoverable because it occurred on Earth. The same failure aboard a generation ship 300 years into its voyage would be recoverable only if the crew possessed the specific knowledge, equipment, and materials needed to address it. If any link in that chain was missing, whether through knowledge loss across generations, equipment degradation, or material depletion, the failure would not be an experimental setback, it would be an extinction event. A generation ship would face equivalent surprises continuously across its entire operational lifespan. No matter how thoroughly the pre-launch testing is conducted, complex ecosystems produce emergent behaviors that cannot be predicted from the properties of individual components. The interaction between 10,000 species of microbes, dozens of crop plants, recycling filtration systems, atmospheric processes, and human metabolic output creates a web of dependencies so dense that modeling it completely exceeds the capacity of any existing simulation. Each generation of crew will encounter failure modes that the previous generation never saw, because the system's slow chemical and biological drift produces new conditions over timescales longer than individual human observation. Water recycling presents its own cascade of compounding challenges. A closed water system must purify all liquid consumed by the crew and all water used in agriculture. This includes metabolic wastewater, agricultural runoff, condensation from atmospheric humidity, and industrial process water, Modern water recycling systems on the International Space Station now recover approximately 98% of water from urine and cabin humidity, a milestone NASA announced in 2023. This is remarkable for a station that still receives regular resupply, but it means 2% of processed water is still lost in each cycle. For a generation ship with no resupply, that 10% loss is a death sentence on a sufficiently long timeline. Even at the current 98% rate, the cumulative 2% loss per cycle would significantly deplete total water reserves within a few decades of operation if no countermeasures existed. In reality, a generation ship would need water recovery rates approaching 99.9% or higher, sustained indefinitely. The purification systems achieving this recovery rate would themselves require maintenance, filter replacement, membrane cleaning, and component repair. The chemicals or biological agents used in purification would need to be manufactured aboard from raw materials. The energy required for continuous water processing would represent a significant fraction of the ship's total power budget, and any interruption in the water recycling chain, whether from equipment failure, contamination, or microbial interference, would begin depleting the single most critical resource aboard within days. Food production aboard a generation ship cannot rely on stored supplies. Preserved food has a finite shelf life even under ideal conditions. Freeze-dried meals lose nutritional value over years. Canned goods degrade over decades. No food preservation technology exists that could maintain edible, nutritionally complete supplies for centuries. The ship must grow virtually all of its food from living agricultural systems, which means it must carry functioning farms that operate without interruption for the entire voyage. These farms face constraints that no terrestrial agriculture has ever encountered. There is no weather, no seasons, no pollination by wild insects, no natural soil replenishment. Every parameter must be artificially controlled, lighting tuned to photosynthetic wavelengths, temperature regulated for each crop variety, nutrient solutions continuously adjusted, pollination performed mechanically or by managed insect populations, pest control maintained without chemical pesticides that would contaminate the closed water and air systems. Crop diversity is essential because human nutrition requires a wide range of vitamins, minerals, amino acids, and fatty acids that no single crop provides. A generation ship must grow grains, legumes, vegetables, fruits, and possibly protein sources such as fish, insects, or cultured cells. Each of these food systems has different requirements for light, water, temperature, nutrients, and growing time. Managing this agricultural complexity in a sealed environment with zero margin for total crop failure represents an agricultural engineering challenge that dwarfs anything attempted in controlled environment agriculture on Earth. And crops fail. On Earth, farmers adapt by switching crops, importing seeds, or allowing fields to lie fallow. A generation ship cannot import seeds or rest its agricultural area because the crew needs to eat every day, and a disease that eliminates one crop variety cannot be stopped by geographic isolation because there is none. The entire agricultural system exists within a single enclosed volume where air, water, and organisms circulate continuously. A fungal blight that enters the wheat section will reach the rice section. Quarantine aboard a sealed vessel is a matter of degree, not kind. Now add radiation. Outside Earth's protective magnetosphere, space is saturated with ionizing radiation from two primary sources. Solar particle events produce intense bursts of protons and heavier ions during solar flares and coronal mass ejections. These events are periodic and partially predictable, occurring more frequently during solar maximum cycles. The second source is galactic cosmic radiation, a constant background of extremely high-energy particles originating from supernovae and other violent astrophysical events throughout the galaxy. Galactic cosmic rays consist primarily of protons, but approximately 1% are heavy ions, such as iron nuclei, traveling at relativistic speeds. These heavy ions carry enormous kinetic energy and are extraordinarily difficult to shield against. Conventional shielding materials like aluminum actually make the problem worse for galactic cosmic rays. When a high-energy heavy ion strikes an aluminum hull plate, it undergoes nuclear spallation, shattering into a shower of secondary particles including neutrons, protons, lighter ions, and gamma rays. This secondary radiation shower can be more biologically damaging than the original particle. The crew is exposed not merely to galactic cosmic rays, but to the secondary cascades generated by those rays interacting with the ship's own hull. Hydrogen-rich materials such as polyethylene or water provide better shielding because hydrogen nuclei absorb proton energy more efficiently without producing as many secondary particles. Some designs propose surrounding the habitat with water tanks, serving the dual purpose of shielding and water storage. This helps against solar particle events, but the highest energy galactic cosmic ray particles carry so much kinetic energy that no practical thickness of any passive shielding material can stop them entirely. An ion nucleus traveling at 90% of the speed of light will penetrate meters of water or polyethylene, leaving a trail of ionization damage through whatever biological tissue it encounters. NASA estimates that astronauts on a Mars mission lasting approximately 3 years would receive a total radiation dose of roughly 1 sievert, which is associated with a 5% increase in lifetime cancer risk. A generation ship traveling for centuries would expose its population to cumulative doses far exceeding this level, unless shielding is dramatically more effective than anything currently achievable. Magnetic shielding, using powerful superconducting magnets to deflect charged particles, has been proposed as an alternative to passive mass shielding. The concept has theoretical merit, but faces practical challenges including the enormous power requirements for maintaining strong magnetic fields, the difficulty of shielding against electrically neutral secondary particles like neutrons, and the engineering challenge of building and maintaining superconducting magnet systems for centuries. The radiation problem is not limited to cancer risk. Research published by NASA's Space Radiation Laboratory has demonstrated that exposure to heavy ion galactic cosmic radiation causes persistent changes in brain structure and cognitive function in animal models. Mice exposed to simulated galactic cosmic ray environments showed reduced hippocampal neurogenesis, impaired synaptic plasticity, and measurable deficits in learning and memory that persisted for months after exposure. These findings suggest that long-duration exposure to galactic cosmic rays may degrade cognitive function in human crews over time, impairing the very mental faculties needed to operate and maintain the ship. Across multiple generations, radiation exposure introduces a genetic dimension. Ionizing radiation damages DNA. While cellular repair mechanisms fix most damage, some mutations escape repair and can be passed to offspring if they occur in reproductive cells. Over centuries of continuous exposure, the generation ship's population would accumulate genetic damage at a rate significantly higher than a population living under Earth's protective magnetosphere. This does not mean the crew would mutate into unrecognizable forms. It means that the background rate of genetic disease, developmental abnormalities, and cancer predisposition would increase with each generation. The ship's medical systems would face a steadily growing burden of radiation-induced illness, with no ability to refer patients to specialized hospitals, no ability to manufacture advanced pharmaceutical compounds beyond whatever the onboard chemistry labs can produce, and no ability to perform medical procedures requiring equipment more sophisticated than what the ship carries. The medical challenge extends far beyond radiation-induced illness. A generation ship must function as its own complete healthcare system for every medical condition that can affect a human population across centuries. This includes trauma surgery for industrial and agricultural accidents, obstetric care for every birth, pediatric medicine for every childhood illness, dental care, ophthalmology, psychiatric treatment, infectious disease management, chronic disease management, geriatric care, and end-of-life palliative care. Every specialty, every diagnostic capability, every surgical procedure, every pharmaceutical compound must be available aboard the ship, or the population goes without. Modern medicine depends on a global supply chain of extraordinary complexity. A single course of antibiotics requires pharmaceutical manufacturing facilities that synthesize active compounds, quality control laboratories that verify purity and dosage, distribution networks that deliver the medication to patients, and a regulatory framework that ensures safety and efficacy. A generation ship must replicate the essential functions of this entire chain using only the equipment and raw materials carried at departure. Pharmaceutical manufacturing aboard a generation ship would require chemical synthesis equipment capable of producing hundreds of different active compounds from base chemicals. It would require analytical instruments to verify the identity, purity, and potency of each compound. It would require sterile compounding facilities to formulate drugs into tablets, liquids, injectables, and other delivery forms. And it would require pharmacological expertise to prescribe, dose, and monitor medications for a population experiencing medical conditions that may differ from terrestrial norms due to radiation exposure, altered gravity, and the unique pathogen ecology of a sealed environment. Surgical equipment presents its own replacement problem. Scalpel blades dull, suture materials are consumed. Imaging equipment, whether X-ray, ultrasound, or magnetic resonance, contains components that degrade and must be serviced or replaced. Anesthesia requires specific chemical compounds that must be manufactured continuously. Sterilization systems consume energy and chemical inputs. Every surgical procedure depletes the ship's medical inventory by a finite amount, and that inventory can only be replenished through onboard manufacturing. The training pipeline for medical professionals must operate without interruption across every generation. Physicians require years of education and supervised clinical experience to become competent. Aboard a generation ship, medical education must be provided by the ship's existing physicians, who are simultaneously providing patient care to the entire population. There is no teaching hospital to rotate through. There are no visiting specialists to learn from. There are no medical journals arriving from a global research community to update knowledge. The ship's medical practice would gradually diverge from terrestrial medicine, developing its own body of clinical experience based on the unique conditions aboard, while potentially losing contact with advances in medical science that occurred on Earth after departure. If a novel disease emerges aboard the ship, whether from mutation of an existing pathogen, from an unexpected interaction between the ship's microbial ecosystem and the human population, or from an environmental contaminant, the medical team must diagnose it, characterize it, and develop a treatment using only the diagnostic and research tools aboard. There is no Centers for Disease Control to consult. There is no World Health Organization to coordinate a response. There is no global pharmaceutical industry to develop a new drug. The ship's medical team is the entire global health infrastructure for their world, and their world contains 20,000 people in a sealed container where airborne pathogens can reach every inhabitant within hours. The engineering systems themselves suffer from radiation damage over these timescales. Ionizing radiation degrades electronic components by displacing atoms in semiconductor crystal structures, altering the electrical properties of transistors and memory cells. Modern radiation-hardened electronics can withstand higher doses than commercial components, but no electronic system is immune to cumulative radiation damage over centuries. The ship's computer systems, sensor arrays, navigation instruments, communication equipment, and control processors would all experience progressive degradation. Replacing damaged electronics requires manufacturing new components aboard the ship, which requires functioning fabrication equipment, which itself is subject to the same radiation damage. This introduces the recursive maintenance problem in its starkest form. Every system on the ship degrades over time through radiation damage, mechanical wear, thermal cycling, chemical corrosion, and material fatigue. Maintaining these systems requires tools, spare parts, raw materials, and technical knowledge. The tools degrade. The spare parts are finite. The raw materials are limited to what was loaded at departure, plus whatever can be recycled from decommissioned equipment. The technical knowledge must be transmitted across generations without loss or distortion. Consider a specific example. The ship's atmospheric recycling system includes centrifugal fans that circulate air through carbon dioxide scrubbers and oxygen concentrators. These fans contain bearings that wear over time. Replacing the bearings requires machined components manufactured to specific tolerances. The machining equipment contains its own bearings, cutting tools, and electronic controllers, all of which also wear and require maintenance. The cutting tools are made from specialized alloys that must be smelted and formed aboard. The smelting furnace requires refractory linings that degrade with each use. At some point, the maintenance chain reaches a component that cannot be manufactured aboard because the ship does not carry the necessary raw materials or because the fabrication equipment needed to produce it has itself failed beyond repair. This is not a hypothetical concern. It is a mathematical certainty. Every manufactured object has a finite number of possible replacements, given a fixed inventory of raw materials and fabrication tools. Over centuries, the number of replaceable components decreases monotonically. The ship's material wealth can only decline. It cannot increase. Every irreversible material transformation, every component that wears beyond recycling, every trace element that becomes chemically locked into an unusable compound represents a permanent deduction from the ship's total resource base. The shipbuilders might address this by carrying enormous inventories of raw materials and building highly versatile fabrication systems. Three-dimensional printing technology, already capable of producing complex metal and polymer components, could theoretically allow a generation ship to manufacture most replacement parts on demand. But three-dimensional printers require feedstock materials, energy, and maintenance of their own precision components. The printers themselves become part of the maintenance recursion, and certain critical materials, rare earth elements used in electronics, specific isotopes used in medical imaging, specialized catalysts used in chemical processing, may be impossible to recycle or substitute once the original supply is exhausted. Structural integrity compounds these concerns over truly long durations. The ship's hull is not merely a container. It is a pressure vessel, a radiation shield, a thermal barrier, and a structural frame simultaneously. It must withstand internal atmospheric pressure pushing outward, the mechanical stresses of any rotational gravity system, thermal gradients between sun-facing and shadow-facing surfaces, and the cumulative impact of micrometeorites. In interstellar space, micrometeorite density is lower than in the solar system, but it is not zero. Over centuries of travel, the hull will absorb thousands of microscopic impacts, each one creating a tiny crater, a stress concentration point, or a microscopic crack in the structural material. Metal fatigue is an insidious failure mode because it produces no visible warning until the moment of catastrophic fracture. Microscopic cracks grow incrementally with each stress cycle. The component appears perfectly functional, then fails suddenly and completely. Aircraft manufacturers manage this through rigorous inspection schedules and mandatory component replacement. A generation ship would need equivalent protocols maintained continuously for centuries across every structural component, every pressure seal, and every rotating assembly. If the ship uses rotation to generate artificial gravity, which virtually all serious generation ship proposals require because prolonged weightlessness causes severe bone loss, muscle atrophy, cardiovascular deconditioning, and immune system impairment, then the rotating sections are subject to continuous centripetal stress. The structural connections between rotating and non-rotating sections must bear the full mechanical load of the habitat's rotation indefinitely. These connections include bearings, seals, and structural couplings that experience constant mechanical wear. A bearing failure in a rotational joint would not merely stop the artificial gravity, it could cause catastrophic structural failure as the rotating section's angular momentum tears it free from the rest of the vessel. The rotation problem deserves closer examination because it determines the physical scale of the entire vessel before any other design consideration begins. Artificial gravity through rotation is not optional. Decades of research aboard the International Space Station have confirmed that prolonged weightlessness produces severe physiological degradation. Bone density decreases by approximately 1 to 2% per month. Muscle mass atrophies despite rigorous exercise regimens. Cardiovascular function deconditions as the heart no longer needs to pump blood against gravity. Intracranial pressure increases, causing vision impairment that has affected a significant percentage of long-duration ISS crew members. The immune system weakens. Wound healing slows. These effects are manageable for missions lasting 6 months to a year, because astronauts return to Earth and recover. A generation ship population lives in its artificial environment permanently. Their children are born into it. Their bones form in it. Their cardiovascular systems develop in it. If the artificial gravity is insufficient or inconsistent, every generation grows up with bodies adapted to conditions that will not match whatever planetary surface awaits at the destination. The physics of rotational gravity impose a punishing constraint on the ship's minimum size. Centripetal acceleration, the force that simulates gravity in a rotating structure, depends on two variables: the rotation rate, and the radius of rotation. To produce one full Earth gravity, a structure with a radius of 100 meters would need to rotate at approximately 3 revolutions per minute. This sounds manageable until you consider the Coriolis effect. In a rotating reference frame, objects moving along the axis of rotation experience a lateral deflection. For a human being walking inside a rotating habitat, this manifests as a persistent sensation that the floor is tilting, that straight-line motion curves unexpectedly, and that the inner ear's balance signals conflict with visual information. The result is motion sickness, disorientation, and impaired coordination. Research on human tolerance to Coriolis effects suggests that most people experience significant discomfort at rotation rates above 2 revolutions per minute, and that sustained habitation becomes problematic above approximately 1.5 revolutions per minute for the general population. Reducing the rotation rate to comfortable levels requires increasing the radius proportionally. To achieve 1 Earth gravity at 1 revolution per minute, the habitat radius must be approximately 900 meters. At half a revolution per minute, which most studies suggest would be comfortable for long-term habitation, including children and elderly residents, the radius must exceed 3,500 meters, 3.5 kilometers. The rotating section of the ship must be at least 7 kilometers in diameter, simply to provide gravity that does not make its inhabitants chronically nauseated. This is not a spacecraft dimension, this is a city dimension. A rotating habitat 7 kilometers across, structurally robust enough to maintain spin for centuries, pressurized against vacuum, shielded against radiation, and connected to the non-rotating sections of the ship through mechanical joints that must bear the full rotational load indefinitely. The structural mass required for such a habitat is staggering. The engineering tolerances for the bearing assemblies connecting rotating and non-rotating sections are measured in fractions of a millimeter across structures spanning kilometers, and every kilogram of structural mass must be accelerated to interstellar velocity, which means every kilogram demands propulsion energy. The generation ship grows larger not because its designers want luxury, but because human biology demands a minimum habitat radius below which long-term habitation becomes medically unsustainable. The ship is enormous because it must be, and its enormity multiplies every other challenge. More structure means more material that can fatigue. More pressurized volume means more atmosphere that must be maintained. More surface area means more hull exposed to micrometeorite impacts and radiation. More rotating mass means more energy consumed maintaining spin. The ship gets bigger while the margin for failure does not grow at all. There is also the question of what happens if the rotation stops. A bearing seizure, a structural fracture in the rotational joint, a power failure to the spin maintenance systems. Any of these events would decelerate the habitat section, reducing artificial gravity over hours or days. The population would experience a gradual transition toward weightlessness, accompanied by the immediate disruption of every system designed for a gravitational environment. Water no longer flows downhill through agricultural irrigation channels. Soil no longer stays in planting beds. The atmospheric convection patterns that distribute heat and humidity cease functioning. Fires, if any occur, behave unpredictably in reduced gravity, forming spherical flame fronts that are harder to detect and extinguish. A loss of rotation is not merely uncomfortable. It is a systemic crisis affecting agriculture, water management, atmospheric circulation, fire safety, and human health simultaneously. Restarting rotation after a stoppage requires enormous energy input and must be performed gradually to avoid subjecting the structure to torque loads it was not designed to withstand in a sudden spin-up. The process could take weeks or months, during which the entire population lives in degraded gravity conditions that accelerate bone loss, muscle atrophy, and cardiovascular deconditioning. If the rotation cannot be restored at all, the mission has effectively ended. Not because the ship is destroyed, but because the crew's long-term health becomes incompatible with the physical demands of arrival and planetary colonization. The thermal environment adds another layer of degradation. In interstellar space, far from any star, the ship must generate all of its own heat. Nuclear reactors are the most plausible power source for a generation ship because they offer the highest energy density and longest operational lifespan of any known power technology. But even nuclear reactors have finite fuel supplies and components that degrade under neutron bombardment. Reactor pressure vessels become embrittled over decades of operation as fast neutrons displace atoms in the steel crystal structure. Control rod mechanisms wear, coolant systems develop leaks, fuel assemblies deplete. Modern nuclear power plants have operational lifespans of 40 to 60 years, with extensive maintenance and periodic refueling from external fuel fabrication facilities. A generation ship reactor would need to operate for 5 to 10 times that duration without an external fuel supply. Breeder reactor designs that produce new fissile material from fertile isotopes could theoretically extend the fuel supply, but breeder technology introduces additional complexity, additional failure modes, and additional radiological hazards. The reactor systems must be maintained by crew members trained in nuclear engineering, a specialized discipline that must be taught and preserved aboard the ship across generations without access to universities, professional licensing bodies, or the accumulated institutional knowledge of terrestrial nuclear industries. The energy budget of a generation ship clarifies just how thin the operational margins become when every system draws from a single finite power source. Consider the major continuous power demands. Agricultural lighting alone represents an enormous energy expenditure. Plants require light intensities comparable to full sunlight for optimal photosynthesis, approximately 1,000 watts per square meter of growing area for the most demanding crops. If the ship must feed 20,000 people using intensive agriculture, the growing area could span hundreds of thousands of square meters, each requiring high-intensity lighting for 12 to 16 hours per day. The electrical power consumed by agricultural lighting alone could reach hundreds of megawatts on a continuous basis. Atmospheric processing adds another major load. Carbon dioxide scrubbers, oxygen concentrators, humidity controllers, temperature regulation systems, and air circulation fans operate continuously across the entire pressurized volume of the ship. Water purification systems pump, filter, distill, and chemically treat every liter of water consumed and excreted by the population, every drop of agricultural runoff, and every volume of industrial process water running without interruption. Waste processing systems break down biological and industrial waste through a combination of microbial digestion, thermal processing, and chemical treatment, each stage consuming energy. Maintaining rotation requires energy input to overcome friction in the bearing assemblies and the gradual transfer of angular momentum through mechanical coupling with non-rotating sections. Fabrication equipment, machine tools, three-dimensional printers, smelting furnaces, and chemical processing systems draw power intermittently but at high peak loads. Medical equipment, communications systems, computing infrastructure, lighting for living and working spaces, and the thermal management systems that prevent the ship from either freezing or overheating in the interstellar void all add to the continuous baseline power demand. A conservative estimate for the total continuous power requirement of a generation ship supporting 20,000 people is on the order of 1 to several gigawatts. This is comparable to the output of a large terrestrial nuclear power plant, but a terrestrial power plant operates within a grid that includes backup generation capacity, fuel resupply from mining and enrichment facilities, and a trained workforce drawn from a national population of millions. A generation ship must produce this power from onboard reactors with no external fuel supply, no backup grid, and a maintenance workforce drawn from a population of 10,000, of whom only a fraction will possess nuclear engineering expertise in any given generation. If reactor output declines by even a small percentage due to fuel depletion, component degradation, or a maintenance shortfall, the power deficit must be allocated across all competing demands. Which system receives less power? The agricultural lights, the water purifiers, the atmospheric processors, the medical equipment. Every reduction in power to any system produces downstream consequences that compound through the ship's interconnected infrastructure. A 5% reduction in agricultural lighting reduces crop yields. Reduced crop yields mean less food and less oxygen production. Less oxygen production increases the load on atmospheric processing systems. Increased atmospheric processing load demands more power from the reactor. The deficit deepens. The spiral tightens. Every one of these challenges, atmospheric recycling, water purification, food production, radiation shielding, structural maintenance, power generation, operates simultaneously and interacts with every other challenge. A failure in the power system reduces the energy available for water purification and atmospheric processing. A failure in atmospheric processing affects crop yields. Reduced crop yields affect nutrition, which affects crew health, which affects the workforce available for maintenance. Reduced maintenance accelerates the degradation of all other systems. The failure modes are not independent, they are coupled, and coupled failure modes in closed systems do not produce linear degradation. They produce cascades. A cascade begins when one system's partial failure increases the load on adjacent systems, pushing them closer to their own failure thresholds. If a second system fails under the increased load, the remaining systems absorb even more stress. Each successive failure accelerates the next. The cascade progresses not at the pace of the initial failure, but at an accelerating rate that can overwhelm the crew's capacity to respond. On Earth, cascading failures in complex systems produce blackouts, industrial accidents, and infrastructure collapses. In each case, the cascade is eventually halted by external intervention, replacement equipment from outside the affected system, emergency personnel from neighbouring jurisdictions, resources imported from unaffected areas. Aboard a generation ship, there is no external intervention. There is no neighbouring jurisdiction. There are no unaffected areas. The cascade either stops because the crew manages to arrest it using only the resources and knowledge available on board, or it continues until it reaches a system whose failure is incompatible with crew survival. The oxygen stops flowing, the water stops being purified, the food stops growing, the hull integrity fails. Any one of these endpoints is fatal, and the margin separating a manageable partial failure from a fatal cascade may be narrower than anyone can predict in advance. The engineering reality of a generation ship is not a single dramatic challenge that can be heroically overcome. It is an accumulation of slow erosions, each individually manageable in the short term, each collectively lethal over the timescales involved. The ship does not explode. It does not collide with an asteroid in a cinematic fireball. It slowly, imperceptibly, inevitably runs down, like a clock with no one to wind it, in a room with no door to the outside. And everything described so far assumes a crew that is competent, motivated, organised, and unified in its commitment to maintaining the ship. It assumes that the people aboard possess the technical knowledge to diagnose failures, the manufacturing capability to produce replacements, and the social cohesion to allocate resources and labour effectively across the entire population. It assumes, in other words, a functioning civilization. What happens when that assumption fails is where the generation ship concept encounters its deepest and most terrifying challenge. Because the machine can be designed on paper, but the people who must keep it running across centuries cannot be designed at all. And what happens to human societies sealed inside a world they cannot leave, travelling toward a destination they did not choose, inheriting a mission they may no longer understand, is a question that no blueprint has ever answered. Every challenge described so far assumes something that has never existed. A human population that remains perfectly cooperative, technically competent, socially stable, and psychologically resilient across centuries of sealed confinement, with no external contact, no escape, and no choice. The engineering problems are severe. The ecological problems are potentially fatal. But both categories of problem share a common feature. They can, at least in principle, be modelled, tested, and designed against using physics, chemistry, and biology. The human problems that a generation ship must solve cannot be modelled with equivalent precision because they involve the one variable that no equation has ever reliably predicted: how people behave when they are trapped. The population question comes first because it constrains everything else. A generation ship cannot carry an arbitrary number of people. Every additional person requires more oxygen, more water, more food, more living space, more waste processing capacity, and more mass that must be accelerated to interstellar velocity. The energy cost of the mission scales roughly with the total mass of the ship, and crew mass is a significant fraction of that total when you account for the life support infrastructure each person requires. There is an overwhelming incentive to minimize the population. but genetics imposes a hard floor on how small that population can be. When a small group reproduces in isolation over many generations, two related processes erode genetic health. Genetic drift randomly eliminates gene variants when too few carriers exist to pass them forward. Over multiple generations, drift strips away diversity like wind eroding stone. Inbreeding compounds the damage. In a small, closed population, individuals inevitably become related within a few generations. Mating between relatives increases the probability that offspring inherit two copies of harmful recessive genes. The consequences accumulate with each generation: reduced fertility, increased infant mortality, higher rates of congenital disease, weakened immune function. These effects have been documented extensively in isolated human populations on Earth. The Pitcairn Islanders, descended from the 9 Bounty mutineers and 18 Polynesian companions who settled the island in 1790, maintained a population of roughly 50 to 200 people for over 2 centuries. Despite their small founding group, they survived. But medical surveys revealed elevated rates of certain genetic conditions, consistent with inbreeding in a small founder population. The inhabitants of Tristan da Cunha, the most remote inhabited island on Earth, descended from 15 original settlers, and after 2 centuries showed elevated rates of asthma, traceable to 3 founders who carried the predisposition. Both cases involved populations that were small but not sealed. Occasional immigration introduced fresh genetic material that partially offset inbreeding effects. A generation ship has no immigration, 0. The founding population is the entire gene pool for the duration of the voyage. No new genetic material enters the system until arrival at the destination, which may be centuries away. This makes the genetic constraints far more severe than any terrestrial analogy suggests. Anthropologist John Moore estimated that a minimum founding population of approximately 160 people, carefully screened and structured into age-balanced reproductive groups, with enforced marriage rules to minimize inbreeding, could sustain genetic diversity for a 200-year voyage. But Moore's estimate assumed optimal social compliance, meaning every individual follows prescribed mating rules across every generation without deviation. It assumed no catastrophic population losses from disease, accident, or conflict. It assumed that the social engineering required to enforce reproductive pairing across centuries actually works. Anthropologist Cameron Smith challenged this optimistic figure in research published for Project Hyperion. Smith's analysis incorporated realistic assumptions about demographic variability, catastrophic mortality events, and the statistical likelihood that some individuals would not reproduce due to infertility, choice, or early death. His models suggested that a genetically safe founding population for a multi-generational voyage would need to be on the order of 14,000 to 44,000 people, with a recommended figure of approximately 20,000 to 40,000. Not because the minimum theoretical number is that high, but because real populations experience shocks, and a population must be large enough to absorb those shocks without falling below viability thresholds. Consider what a population of even 20,000 means for the ship, using the lower end of Smith's recommended range. 20,000 people require living space, workspace, recreational space, agricultural space, industrial space, medical facilities, educational facilities, and governance infrastructure. They generate waste, consume resources, and require social structures complex enough to manage conflicts, allocate labor, enforce laws, and maintain order. 20,000 people are not a crew. It is a small city. And small cities on Earth, with all the advantages of open air, natural ecosystems, external trade, and the psychological comfort of knowing the world extends beyond the city limits, still experience crime, political instability, resource disputes, and social fragmentation. A generation ship carrying 10,000 people must govern that population under conditions of absolute material constraint and permanent confinement. Governance aboard such a vessel faces a problem that no political system in human history has been designed to solve. The government must persist across centuries with no external legitimacy, no electoral comparison to alternative systems, no immigration or emigration to release social pressure, and no possibility of secession by dissatisfied factions. Every political system humanity has invented relies on at least one of these pressure valves. Democracies survive partly because dissatisfied citizens can vote, protest, emigrate, or form opposition parties. Monarchies survive partly because dynastic legitimacy draws on religious or cultural traditions, reinforced by external relationships with other kingdoms. Even authoritarian regimes maintain stability, partly through the implicit threat that citizens who cannot flee will be controlled by force, a strategy that depends on the rulers having access to resources and manpower sufficient to enforce compliance. Aboard a generation ship, the dynamics of governance become pathological. If the system is democratic, what happens when a majority votes to change the mission, to turn the ship around, to abandon the destination and simply live aboard indefinitely? The founders designed the mission. The seventh generation inherited it. What right does the founding generation have to bind the political choices of their descendants across centuries? On Earth, constitutions are amended, laws are repealed, revolutions occur. The political commitments of one generation do not permanently bind the next, because future generations retain the power to change course. A generation ship whose mission cannot be altered by its inhabitants is a dictatorship of the dead over the living. A generation ship whose mission can be altered by its inhabitants may see that mission abandoned by people who feel no connection to a destination chosen by ancestors they never knew. If the system is authoritarian, the standard risks of authoritarian governance are magnified by confinement. Power corrupts. Concentrated power in a sealed environment with no external oversight and no possibility of regime change through emigration or foreign intervention corrupts absolutely and permanently. A tyrannical captain or ruling council aboard a generation ship cannot be removed by external pressure because there is no external anything. Oppressed populations on Earth can flee across borders, appeal to international bodies, or receive support from outside allies. Oppressed populations aboard a generation ship have no borders to cross, no international bodies to petition, and no outside allies who even know they exist. Religious or ideological governance might offer more stability by grounding authority in transcendent principles rather than individual leaders. Several generation ship proposals have suggested founding the mission around a shared religious or philosophical framework strong enough to maintain social cohesion across generations. History provides partial support for this idea. Religious communities such as certain monastic orders and tightly knit sectarian groups have maintained institutional continuity for centuries. The Benedictine monastic tradition, founded in the 6th century, persists today. Certain Jewish communities maintained cultural and religious identity across millennia of diaspora, but these examples survived within larger civilizations that provided economic support, cultural context, and a continuous flow of new members. A generation ship religious community would exist in total isolation. There would be no broader civilization to contextualize the faith, no influx of new converts to renew enthusiasm. The religion would need to sustain meaning and authority entirely from within, across generations experiencing no contact with anything outside the hull. A sealed religious community would face intellectual stagnation, doctrinal rigidity, or schism, the same three fates that have befallen every isolated religious community in recorded history. Cultural transmission compounds the governance challenge. The skills, knowledge, and institutional memory required to maintain the ship must be passed from each generation to the next without degradation. This is not limited to technical knowledge about reactor maintenance and atmospheric chemistry. It includes the entire framework of social norms, historical understanding, and mission context that gives the voyage meaning and structure. On Earth, cultural transmission occurs through a vast ecosystem of institutions. Schools, universities, libraries, museums, media organizations, professional associations, apprenticeship systems, and informal community networks all contribute to preserving and transmitting knowledge across generations. These institutions are redundant. If one fails, others compensate. If a university closes, its knowledge persists in books, in the memories of its graduates, in competing institutions, and in the broader intellectual culture. A generation ship must replicate these functions with a fraction of the institutional infrastructure and zero redundancy from external sources. The fragility of knowledge transmission in isolated communities has been documented repeatedly. The Tasmanian Aboriginals, isolated from the Australian mainland for approximately 10,000 years after rising sea levels severed the land bridge, gradually lost several technologies that their ancestors had possessed, including the manufacture of bone tools and the construction of cold-weather clothing. Some researchers have also argued that they lost the ability to start fire independently, though this claim remains debated among anthropologists. This technological regression occurred not because the Tasmanians were less intelligent than their mainland counterparts, but because their small, isolated population could not maintain the full breadth of specialized knowledge that a larger, interconnected population preserves through distributed expertise and redundant transmission pathways. A generation ship faces an equivalent risk. Specialized technical knowledge is maintained by specialists. If the ship's nuclear engineering team is small, perhaps 5 or 10 people in a given generation, and a disease outbreak or accident kills several of them before they have fully trained replacements, that knowledge is diminished or lost. The loss may not be immediately apparent. The reactor continues operating on its existing maintenance schedule, but when a novel failure mode emerges 2 generations later, the crew may lack the deep institutional knowledge to diagnose and repair it, because the chain of expert transmission was broken decades earlier. Language itself will drift. Linguists have established that all living languages change continuously through phonological shifts, grammatical simplification or complexification, vocabulary evolution, and semantic drift. The rate of change depends on population size, social structure, and contact with other language communities. Isolated populations experience faster linguistic drift because there are fewer speakers to enforce conservative norms. Research published in connection with generation ship studies has estimated that a sealed shipboard population would develop a distinct dialect within a few generations and a potentially mutually unintelligible language within 10 to 20 generations. This linguistic drift has practical consequences beyond cultural curiosity. Technical documentation written by the founding generation would become increasingly difficult for later generations to read. Operating manuals, engineering specifications, safety procedures, and scientific records would gradually become archaic texts, requiring translation rather than direct comprehension. Unless the ship maintains a rigorous program of language standardization enforced across centuries, the technical literature that preserves critical maintenance knowledge would slowly become inaccessible to the very people who need it most. Children complicate the generation ship in ways that no other category of inhabitant does, because children must be formed entirely by the environment aboard. An adult who boarded the ship at launch carries memories of Earth, of open landscapes, of cultural variety, of a world with horizons. A child born in Generation 4 carries none of this. Their entire cognitive and emotional development occurs within the ship's interior. Their concept of normal is the ship. Their understanding of the world is shaped entirely by artificial environments, recycled air, engineered lighting, and a social universe limited to the same few thousand faces they have known since birth. Developmental psychology has established that children's cognitive and emotional growth is profoundly shaped by environmental richness. Exposure to natural environments improves attention, reduces stress, and supports the development of spatial reasoning and creativity. Variety in social interactions builds theory of mind, the ability to understand that other people have different perspectives and beliefs. Exposure to diverse cultural practices fosters cognitive flexibility and adaptive thinking. A generation ship can attempt to simulate some of these inputs through designed green spaces, varied architectural environments, and structured social programs. But the simulation is bounded by the ship's finite volume and population. A child growing up aboard a generation ship will never see a horizon. The longest unobstructed sightline inside even a very large rotating habitat might be a few hundred meters. They will never experience weather that was not programmed. They will never encounter an animal that was not deliberately included in the ship's ecosystem. They will never meet a stranger, in the deepest sense of that word, because every person aboard is part of the same small community and has been known, at least by reputation, since before the child was born. The educational challenge is even more acute. The ship needs every generation to produce a specific distribution of skilled professionals. Life support engineers, agricultural specialists, nuclear technicians, physicians, fabrication machinists, computer systems administrators, teachers, and governance personnel. The population is too small to support a free labour market where individuals choose careers based on interest and aptitude. The ship needs specific roles filled in specific numbers, and educational systems must be designed to channel children toward those roles, whether or not individual children find them compelling. On Earth, educational systems can afford inefficiency because the economy is large and diverse enough to absorb people who change careers, pursue impractical interests, or fail to develop marketable skills. A generation ship cannot afford this flexibility. If too few children choose to study nuclear engineering, the reactor maintenance team shrinks in the next generation. If too many children pursue artistic or humanistic interests at the expense of technical training, the ship's operational capacity degrades. Education aboard a generation ship is not a path to personal fulfillment. It is a resource allocation mechanism, and children are the resource being allocated. This creates a tension between individual autonomy and collective survival that no educational philosophy has resolved. Do you allow children to follow their interests and risk critical skill shortages? Or do you assign educational tracks based on aptitude testing and ship needs, producing a technically competent workforce at the cost of personal freedom and intrinsic motivation? The first approach risks the ship's operational capacity. The second approach risks producing a population of resentful workers performing duties they did not choose, which degrades the social cohesion the ship depends on for long-term survival. Teaching children about the destination presents its own pedagogical puzzle. How do you convey the significance of a planet that no living person has visited, that exists only as data in astronomical records compiled by people who died generations ago? How do you motivate a 12-year-old to care about a world they will never reach, when the world they actually inhabit, the ship, is the only reality they have ever known? How do you prevent the destination from becoming an abstraction so remote from daily experience that it loses all motivational force? Earth-based education draws constantly on experiential reference points. A geography lesson invokes landscapes the student might someday visit. A biology lesson can be supplemented by a walk in a forest. A history lesson describes events that occurred in places that still exist and can be travelled to. Aboard a generation ship, every reference to the world outside the hull is second-hand. Every description of a planet, an ocean, a mountain range, a thunderstorm, is mediated through recordings, simulations, and inherited narratives. The educational system must somehow transmit not just information but felt significance about realities that no living person aboard has directly experienced. If it fails, if the destination becomes just a word in a curriculum rather than a felt aspiration, then the motivational foundation of the entire mission erodes at its source. The adults who lose faith in the mission were once children who were never given a reason to believe in it that felt real. The mission does not die in a dramatic moment of collective rejection. It dies quietly, in a classroom, when a child asks why they should care about a star they will never see, and the teacher does not have an answer that resonates. Mission drift is the overarching term for all of these processes, and it is perhaps the single most likely mode of failure for a generation ship that survives its engineering challenges. Mission drift occurs when the original purpose of an institution gradually shifts, dilutes, or disappears as the people carrying out that purpose are replaced by successors with different experiences, priorities, and values. Every long-lived institution on Earth has experienced mission drift. Universities founded to train clergy now teach engineering and business. Military orders founded for holy war now operate hospitals and charities. Colonial outposts founded for resource extraction became independent nations with no allegiance to the founding power. These transformations are not failures in a terrestrial context. They represent healthy institutional adaptation to changing circumstances. But aboard a generation ship, mission drift is catastrophic because the mission is the reason the ship exists. If the 8th generation no longer understands, values, or prioritizes reaching the destination star, the entire rationale for the voyage dissolves. The ship becomes not an ark carrying humanity to a new world, but a sealed habitat drifting through interstellar space with no purpose beyond its own perpetuation. And perpetuation without purpose creates its own psychological crisis. Human beings derive meaning from goals, from narratives that explain suffering and justify sacrifice. The founding generation of a generation ship possesses a powerful narrative. They are pioneers, explorers, saviors of the species perhaps. If the mission is framed as a survival imperative, they chose this. They believe in the destination. They can endure the hardship because they understand why it is necessary. Their children inherit a diluted version of this narrative. They heard the stories, they were raised on the mythology of the mission, but they never stood on Earth. They never felt sunlight that was not artificial. They never breathed air that was not recycled. The destination is an abstraction taught in classrooms, not a felt reality. Their commitment to the mission is second-hand, inherited, doctrinal rather than experiential. By the 5th or 6th generation, the narrative has become mythology in the anthropological sense, a foundational story that explains the community's existence, but may or may not be taken literally. Some members of the community may passionately believe in the mission, others may regard it as a quaint tradition. Still others may actively reject it, arguing that the ship is their home and the destination is irrelevant, unnecessary, or even dangerous. Why risk landing on an alien world when the ship has sustained them for generations? Why change what works? This is not speculative psychology. It is the documented behavior of every long-duration isolated community in human history. The Polynesian voyaging cultures that settled the Pacific Islands maintained their navigation knowledge only as long as active voyaging continued. When island populations became self-sustaining and the impetus to explore diminished navigation knowledge was lost within a few generations, the skills survived in oral tradition as ceremony rather than practice. European explorers eventually encountered communities that possessed ancient canoe designs in their mythology, but no living practitioners who could build or navigate them. A generation ship faces the same trajectory. The skills needed for arrival, planetary survey, atmospheric entry, surface colonization are not the skills needed for the voyage itself. If the voyage lasts 10 or 15 generations, the arrival skills have no practical application for hundreds of years. They exist only in training programs and documentation. Maintaining proficiency in skills that will not be used for centuries requires extraordinary institutional discipline. It requires each generation to invest significant resources in training for an event that will not occur in their lifetime or their children's lifetime or their grandchildren's lifetime. History suggests this level of sustained investment in deferred outcomes is extremely rare, even in well-resourced societies with strong institutional frameworks. The psychological burden of inherited exile deserves its own attention because it operates at the individual level, beneath the institutional and cultural dynamics described above. Consider the experience of a person born on a generation ship in, say, Generation 7. This person has never seen Earth, has never seen any planet, has never experienced weather or an ocean or an unconfined horizon. Their entire world is a structure approximately the volume of a small town, surrounded by walls beyond which lies instant death. Every person they will ever meet already lives in this structure. Every experience they will ever have will occur within this structure. They will die within this structure. This person did not volunteer for this existence. They were born into it, the product of a reproductive decision made by their parents within the constraints imposed by a mission designed by people who died generations ago. Their autonomy is bounded by the ship's resource limitations, governance structure, and social expectations in ways that no terrestrial citizen experiences. They cannot change careers freely because the ship needs specific roles filled. They cannot choose to have more or fewer children than the population management plan allows. They cannot opt out of the community because there is no outside. On Earth, even prisoners know that the world continues beyond their cell walls. Inmates can imagine a future outside confinement. Many can work toward release. The psychological architecture of imprisonment depends on the existence of an outside, a world that continues in the prisoner's absence and to which they might someday return. Generation ship inhabitants have no such outside. The ship is not a temporary confinement, it is a permanent reality. There is no release date. There is no parole. There is no world beyond the hull that they could reach even if they wanted to. The psychological literature on long-duration confinement in isolated environments, drawn from submarine deployments, Antarctic winter overstations, and simulated Mars missions such as the Mars 500 experiment, consistently identifies a cluster of psychological responses including depression, interpersonal conflict, social withdrawal, sleep disruption, cognitive impairment, and what researchers call third quarter syndrome, a motivational collapse that occurs roughly 3/4 of the way through a confinement period when the end is visible but still distant. These studies involve confinement periods ranging from 6 months to approximately a year and a half. The generation ship requires confinement periods of an entire lifetime, repeated across multiple lifetimes, with no end visible for most of the voyage. Nuclear propulsion concepts improve the ratio but do not solve it. Project Orion, studied in the late 1950s, proposed riding nuclear detonation shockwaves to a few percent of light speed, but was abandoned after the Limited Test Ban Treaty of 1963. More exotic proposals exist: fusion drives, antimatter propulsion, laser-pushed light sails. Breakthrough Starshot, announced in 2016, aims to use ground-based lasers to accelerate gram-scale probes to 20% of light speed, reaching Proxima Centauri in about 20 years, but the probes weigh only a few grams. Extrapolating from 6-month confinement studies to multi-generational confinement is methodologically risky. The psychological dynamics of permanent confinement may differ qualitatively, not just quantitatively from temporary confinement, but the direction of the evidence is unambiguous. Confinement degrades psychological function. Isolation amplifies interpersonal conflict. Resource scarcity intensifies competition, and the absence of external novelty, new places, new people, new experiences produces a flattening of affect and motivation that accumulates over time. Now multiply these individual psychological burdens by the population of the ship and project them across centuries. A community of 10,000 people experiencing chronic low-grade psychological distress, generational resentment toward an inherited mission, governance structures straining under the pressure of permanent confinement, and cultural drift eroding the institutional memory needed to maintain the ship. This is not a crew operating a spacecraft. This is a captive civilization under permanent strain, asked to maintain perfect technical discipline and social cohesion for longer than most civilizations have endured under vastly more favorable conditions. The historical record is clear. No human civilization has ever maintained stable governance, continuous cultural transmission, and unbroken institutional purpose for the duration required by even the shortest plausible generation ship voyage. The Ottoman Empire endured for over 6 centuries, but survived through continuous territorial expansion, absorption of conquered peoples, and periodic internal reform driven by contact with rival powers. The Catholic Church has persisted for roughly 2,000 years, but has experienced schisms, reformations, corruption scandals, and doctrinal revolutions that would have been fatal in a sealed environment with no room for institutional competition. Chinese dynastic civilization maintained cultural continuity across millennia, but did so through a cycle of collapse and reconstruction, with each dynasty replacing the last through war, revolution, or internal disintegration. Every long-lived civilization on Earth survived by adapting, absorbing external influences, recovering from catastrophic disruptions through contact with neighboring cultures, and allowing its population the fundamental freedom to leave. A generation ship permits none of these survival mechanisms. It is a closed system in every sense, materially, socially, culturally, and psychologically. The very qualities that make civilizations resilient on Earth, openness, adaptability, exchange, redundancy through diversity, are precisely the qualities that a sealed interstellar vessel cannot provide. The ship's engineering may function perfectly, the reactors may hum, the atmosphere may remain breathable, the crops may grow, the water may flow clean, and inside this functioning machine, the civilization it was built to carry may slowly, quietly, inevitably come apart. Not through a single dramatic crisis, but through the accumulated weight of isolation, confinement, drift, and the unbearable inheritance of a mission that belongs to the dead imposed upon the living. And this realization leads to the deepest question the generation ship concept forces us to confront. A question that is not about engineering, or ecology, or genetics, or governance. A question about what it means to ask a human society to survive under conditions that no human society has ever survived, for for longer than any human society has ever lasted, with no margin for the kind of failure that every human society has eventually experienced. That question and its answer is what makes the generation ship not merely difficult, but genuinely terrifying. Everything we have examined so far has followed a single trajectory, a narrowing. The ecological margins tighten, the engineering tolerances shrink, the social fabric thins, the psychological reserves deplete. And what remains, after every system has been calculated and every structure tested against history, is a question so fundamental that it precedes every technical specification and survives every engineering solution. Can a human civilization be built to order and expected not to fail? Not a machine, not an ecosystem, not a government, a civilization. The full architecture of human collective existence. Language, memory, purpose, trust, knowledge, cooperation, identity, meaning. All of it sealed inside a container, launched into darkness, and asked to persist without interruption for longer than most of the civilizations that have ever existed on Earth. The Roman Empire is often cited as an example of institutional longevity. It endured, in its Western form, for roughly 5 centuries, and in its Eastern continuation as the Byzantine Empire, for nearly 15 centuries in total. But the Roman Empire that fell in 476 bore almost no resemblance to the Republic that preceded the Empire, which bore limited resemblance to the early kingdom, which bore little resemblance to the small settlement on the Tiber that tradition places in 753 BCE. Roman civilization persisted not by remaining stable, but by transforming continuously. It absorbed new peoples, adopted new religions, reformed its governance structures, expanded and contracted its borders, survived civil wars and plagues and invasions, and reinvented itself repeatedly across the centuries. Each transformation was enabled by contact with the broader world, by the influx of new ideas, new populations, new resources, and new pressures that forced adaptation. A generation ship cannot transform in these ways. It cannot absorb new peoples. It cannot adopt new resources. It cannot expand its borders because the hull is the border and the hull does not grow. The only adaptive mechanism available is internal reorganization. And internal reorganization in a closed system is zero-sum. Every change that benefits one group disadvantages another. The political, social, and material flexibility that allowed terrestrial civilizations to survive across centuries is precisely what a generation ship cannot possess. This is not a limitation that better engineering can overcome. It is a structural feature of the concept itself. A generation ship is defined by its closure. It is sealed materially, sealed socially, sealed informationally. Nothing enters, nothing leaves. The system must generate all of its own stability from internal reserves, and internal reserves are finite by definition. Every conflict that is resolved consumes social capital that cannot be replenished from outside. Every material crisis that is overcome depletes physical reserves that cannot be restocked. Every generation that maintains cohesion does so by drawing on cultural and institutional deposits that are being steadily diminished by the very act of sustaining the community. Think of it as an inheritance that can only be spent, never earned. The founding generation deposits social trust, shared purpose, technical knowledge, and institutional legitimacy into the ship's collective account. Each subsequent generation withdraws from that account. If the withdrawals are modest, the balance can last for many generations, but the account earns no interest and cannot be supplemented externally. Every crisis, every conflict, every failure of transmission accelerates the rate of withdrawal. The question is not whether the balance eventually reaches zero. Given enough time, it must. The question is whether the balance reaches zero before the ship reaches its destination. And the answer depends on variables that no one can reliably predict before departure. How severe will the crises be? How effective will the conflict resolution mechanisms prove? How faithfully will knowledge be transmitted? How much social capital will be consumed by each generation's internal struggles? These questions involve the behavior of human beings across centuries under conditions that have never existed, and they cannot be answered by simulation, by historical analogy, or by design. This is where the generation ship concept reveals its deepest and most unsettling implication. The ship is not the hard part. The civilization is the hard part. And the civilization is the part that cannot be engineered. Engineers can design a hull that withstands micrometeorite impacts for centuries. They can design a reactor that produces power for millennia. They can design an atmospheric recycling system that maintains breathable air with 99.9% efficiency. Each of these is a staggering technical achievement, but each falls within the domain of physics and materials science, where problems have solutions, and solutions can be verified through testing. The civilization that must operate these systems, maintain them, repair them, and transmit the knowledge required to do so across generations does not fall within any equivalent domain. There is no science of civilization construction. There is no tested methodology for building a human society from scratch and guaranteeing its stability across arbitrary timescales. History offers no usable template because every civilization that has endured for centuries did so under conditions fundamentally different from those aboard a generation ship. Open borders, contact with neighbors, access to natural resources, the ability to expand geographically, the psychological safety of inhabiting a world with horizons. Remove all of these and you are not studying civilization as it has existed. You are studying something that has never existed. A sealed, artificial, involuntary society with no external reference points and no exit. The closest terrestrial analogies are prisons, monasteries, and isolated island communities, and none of them are encouraging. Prisons maintain order through external authority backed by a surrounding state. Remove the state, and the prison becomes ungovernable. Monasteries maintain purpose through religious devotion, but they exist within a broader tradition that provides context and a continuous supply of voluntary new members. Remove the tradition, and the monastery becomes a relic. Isolated island communities persist for generations, but they exist on planets with atmospheres and ecosystems that buffer survival against local failures. Remove the planet, and the community dies. A generation ship combines the confinement of a prison, the insularity of a monastery, and the isolation of a remote island, while removing every external support system that allows each of these institutions to function. It is the most demanding social experiment ever conceived, conducted under conditions deliberately designed to eliminate every mechanism that has historically allowed human societies to recover from failure. And the experiment cannot be restarted. There is no second attempt. If the civilization fractures in Generation 6, there is no external mediator to negotiate peace. If critical knowledge is lost in Generation 10, there is no university to consult. If the population collapses below genetic viability, there is no immigration to restore the gene pool. Every failure is permanent. Every loss is irreversible. The ship carries no eraser. This permanence distinguishes the generation ship from every other human endeavor. On Earth, civilizations fail all the time. They collapse, fragment, are conquered, or transform beyond recognition. And when they do, the human species continues. Other civilizations exist. Other populations carry forward the accumulated knowledge and cultural heritage of the species. The fall of Rome did not erase Roman knowledge because Byzantine scholars, Islamic translators, and European monks preserved fragments that were eventually reassembled during the Renaissance. The collapse of the Maya civilization did not erase human achievement because the Maya existed alongside thousands of other cultures that continued developing independently. A generation ship is alone. If its civilization fails, there is no neighboring civilization to preserve its knowledge. There is no successor state to rebuild from the ruins. There is only the ship, drifting through interstellar space, carrying a population that may have lost the ability to maintain the systems keeping them alive. The failure of civilization aboard a generation ship is not an abstract historical event. It is a death sentence carried out in slow motion across generations, as the descendants of the original crew gradually lose the capacity to sustain the artificial world their ancestors built. This scenario, a ship that functions mechanically while failing humanly, may be the most likely outcome of any generation ship attempt. The hull holds, the reactors produce power, the atmospheric processes continue cycling. But the people inside have fractured into competing factions, or have lost the technical knowledge to perform critical repairs, or have abandoned the mission in favour of a static existence aboard the vessel, or have descended into authoritarian control. that prioritizes the regime's survival over the mission's completion. The ship arrives at its destination with a population that cannot land, cannot survey the target world, cannot construct a colony, and may not even understand what the destination is or why their ancestors launched toward it. Science fiction has explored this scenario repeatedly because writers recognized its narrative power and its plausibility long before engineers confronted its implications. Robert Heinlein's Orphans of the Sky, originally published as 2 novellas in 1941, depicted a generation ship whose inhabitants have forgotten they are on a ship, believing the vessel to be the entire universe. Brian Aldiss's 1958 novel Non-Stop portrayed a similar amnesia, with the ship's descendants living as tribal hunter-gatherers inside a vessel they no longer comprehend. These stories are not merely imaginative. They are extrapolations of documented human behavior in isolated communities projected onto the generation ship timescale. The ancestral Puebloan civilization of the American Southwest built elaborate cliff dwellings and sustained a complex agricultural society for centuries before prolonged drought, resource depletion, and social fragmentation drove total abandonment by the late 13th century. The Rapa Nui civilization on Easter Island deforested their entire island, collapsed their ecosystem, and descended into warfare and population crash. The Norse colony in Greenland persisted for roughly 4.5 centuries before failing entirely, its last inhabitants starving in a landscape they could no longer sustain themselves within. Each of these cases involved populations with access to open air, sunlight, natural water, biological ecosystems, and the psychological grounding of living on a planet. Each nonetheless experienced severe cultural regression, knowledge loss, or civilizational collapse. A generation ship offers none of these environmental supports. It demands that a human community maintain perfect institutional continuity in an environment specifically designed to test every psychological and social limit simultaneously. The radiation keeps falling. That fact deserves emphasis because it illustrates how physical and human burdens interact across generational time. Galactic cosmic ray exposure does not stop because the crew is experiencing a political crisis. DNA damage does not pause because the medical team lost a critical specialist to an accident. Cancer rates do not plateau because the population is struggling with food shortages. The radiation is constant, indifferent, cumulative. Each generation is slightly more damaged than the last. Each generation faces a slightly higher burden of chronic illness, a slightly smaller pool of healthy workers, a slightly greater demand on medical resources that are themselves degrading. Over 5 or 10 generations, this cumulative biological erosion may remain manageable. Over 20 or 30 generations, it compounds into a systemic drag on the population's capacity to maintain the ship. More people are sick. More labor hours go to caregiving. Fewer skilled workers are available for critical maintenance. The genetic burden reduces the effective population below the number physically present aboard. A ship carrying 20,000 people in Generation 15 might have only 14,000 healthy enough to work, and of those 7,000, only a fraction possess the specialized skills needed for reactor maintenance, atmospheric calibration, or agricultural management. This is the convergence point where every category of burden meets. The engineering systems degrade, the ecological margins narrow, the genetic health declines, the social structures strain, the cultural memory fades, the psychological resilience erodes, and each of these processes accelerates the others. Sicker people maintain systems less effectively. Poorly maintained systems produce more environmental stress. Environmental stress worsens health outcomes and intensifies social conflict. Social conflict disrupts governance and knowledge transmission. Disrupted knowledge transmission leads to less effective maintenance. The spiral tightens with each generation, and the resources available to arrest it diminish at exactly the same rate. No single one of these burdens is necessarily fatal on its own. A well-designed ship might survive a period of social instability. A robust population might endure a radiation-induced increase in cancer rates. A skilled engineering team might manage a cascade of mechanical failures. But the generation ship does not face any single burden in isolation. It faces all of them simultaneously, continuously, and cumulatively for centuries. The question is not whether any individual challenge can be overcome. The question is whether all of them can be overcome at once by the same population using the same finite resources across a timescale that exceeds every comparable human achievement. And here is the thought that should keep you awake. The generation ship concept is not wild speculation. It is the most physically plausible method of interstellar human migration using known physics. Cryogenic sleep does not exist. Relativistic travel demands impossible energy. Faster-than-light travel violates established physical law. If humans are ever to reach another star in physical form, the generation ship, or something functionally equivalent to it, is what the laws of physics require. The brutal reality is not that generation ships are one option among many. The brutal reality is that generation ships may be the only option, and the only option may be functionally impossible. Not impossible because we cannot build the ship. We probably can, given sufficient resources and political will, within a few centuries of continued technological development. The materials science is challenging, but not implausible. The propulsion requirements are enormous, but not beyond what nuclear or fusion technology might eventually provide. The ecological engineering is daunting, but builds on principles that are well understood even if the execution at scale remains undemonstrated. The ship can probably be built. The civilization inside it probably cannot be sustained. This is the inversion that most people never see coming. The brutal reality of generation ships is not a catalogue of engineering challenges that future technology might solve. It is the recognition that the hardest part of interstellar travel has nothing to do with propulsion, materials, or life support. The hardest part is the people. The hardest part is asking a human society to do something no human society has ever done. To survive sealed, isolated, confined, and purposeful for longer than any nation, empire, religion, or cultural tradition has ever persisted without transformation, interruption, or collapse. The first generation ship, if it is ever launched, will carry more than passengers and cargo. It will carry the most consequential experiment in human history, an experiment to determine whether Homo sapiens, a species that evolved on open savannas under limitless skies, can sustain a functioning civilization inside a metal world smaller than a village, crossing a void wider than comprehension for longer than recorded history. The experiment has no control group. It cannot be repeated. Its subjects did not consent, because most of them have not yet been born, and its outcome will be determined not by the strength of the hull, or the efficiency of the reactors, or the yield of the crops, but by something far more fragile and far less understood. The ability of human beings to remain human, to remember who they are and why they are traveling, to maintain trust and cooperation and purpose and meaning across the silence of generations, in a world without horizons, without seasons, without the sound of wind or the sight of an unobstructed sky. Every generation ship proposal is, at its core, a bet. A bet that human nature is robust enough to survive the most extreme isolation ever imposed on a population. A bet that social engineering can achieve what no social system has ever achieved. A bet that the accumulated fragility of closed ecosystems, degrading machinery, cumulative radiation, genetic erosion, cultural drift, and psychological confinement will not, across centuries, produce a failure cascade that transforms the Ark into a tomb. The honest assessment, based on everything we know about human societies, closed ecosystems, material degradation, and population genetics, is that this bet is extraordinarily risky, not impossible. Humanity has surprised itself before, but the margin for success is thinner than almost any generation ship advocate publicly acknowledges, and the consequences of failure are absolute. The stars are not unreachable because they are far away. The stars are unreachable because the bridge we would need to build is not made of metal or fuel or engineering brilliance. It is made of human continuity, of memory, of purpose carried forward by people who did not choose it, through darkness they did not ask for, toward a light they may never see. The generation ship does not fail because the distance is too great. It fails because the distance requires something of us that we have never demonstrated we can sustain. Not speed, not power. Not ingenuity, endurance. The endurance of a civilization that cannot afford a single century of the kind of failure that every civilization in human history has eventually experienced. The void between the stars is vast, but the void inside a sealed ship, the void where meaning and purpose and social cohesion must be continuously manufactured from nothing but human will, may be vaster still. And crossing that interior void, keeping a human world intact and functional and purposeful across the centuries of silence, may be the single most difficult thing our species could ever attempt. The first true interstellar arc, if it is ever built, will not fail because humanity could not cross the distance. It will fail, if it fails, because keeping humanity intact was harder than crossing the distance, because the ship was not the challenge. The civilization was. And civilization, it turns out, is the most fragile machine we have ever tried to build. More fragile than the hull, more fragile than the reactor, more fragile than the atmosphere recyclers and the water purifiers and the crops and the carefully managed gene pool, more fragile than anything aboard, because it is the one system that cannot be repaired with a wrench, cannot be replaced with a spare, and cannot be restarted once it stops. The brutal reality of generation ships is not that they are difficult to build, it is that they ask us to turn a spacecraft into a civilization and then expect that civilization to survive in exile, in isolation, and in fragility for longer than human history has ever sustained anything. And the most terrifying part is not that we might fail, it is that this may be the only way. And we do not yet know if we are the kind of species that can succeed.